Hello, Professor Sargent here with you again for another Math 101 flipped classroom lesson. This is on section 7.1. It could be a long one, so sit tight. And in this section, we take a look at roots, otherwise known as radicals, and we'll be seeing what they are and get a little bit of information about why we use them. So here we have our definition of what the nth root of a is. If you can find a number such that b to the nth power is equal to a, then b is the nth root of a. Our root is a whole number starting with 2. So you'd be talking about a second root or third root or fourth root and so on. That n is called the index. What's underneath the check marky sign called a radical symbol. What's underneath that is called the radicand. You see the index kind of inside the check mark part. And overall, nth root of a is a radical expression. So for example, we have here cube root of 5 or third root of 5. 3 is the index, 5 is the radicand. When you're talking about the square root, since that is so common, the second root is so common that we leave out the index. It's assumed to be a 2 when it's not written. And you also have to take note that that index of n, that is not saying n times the square root of a, it is saying the nth root of a. So why is the nth root of a not a real number if n is even and a is negative? That's going to be one thing that we address. If n is even and a is positive, there are 2 possible choices for the nth roots. We're going to address that. Those 2 possible choices will be, one will be positive and one will be negative. And we will call the one that is positive the principal roots. Now, on the other hand, if n is odd, there's just one choice for the nth root for every real number a as a radicand. So the nth root of a is positive when a is positive, and it is negative when a is negative when you have an odd index. All right, so addressing this part right here first. You take 5 and square it, you get 25. But also when you take negative 5 and square it, notice how I've got parentheses there. Before we do the squaring, that negative 5 is in parentheses. That means that all of that expression, negative 5, is being squared. Negative 5 times itself, another negative 5, is going to be positive 25. So because of that, both 5 and negative 5 are square roots of 25. However, we would say that 5 is the principal square root of it. And similarly speaking, 6 to the 4th is equal to 1,296. On a TI-30, instead of doing 6 times 6 times 6 times 6, we could do 6. 4th power is right there. There's the 1,296. You may have an older calculator that doesn't show the exponent quite as nicely. So it would look like this. Anyway, I'm going to switch the mode back because that's going to let me show something really nice later on. So we're going to the math print mode and then I quit. All right. Well, also negative 6 to the 4th power. You get your negative sign on a TI-30 down here. Not the same as using the minus sign. Negative 6 to the 4th power, also giving us 1,296. So that's telling us that the we have two different answers for the fourth root of 1,296, but the principal one is the positive one. So usually when people say, what's the fourth root of 1,296, people would say 6, because a lot of people are going to assume that we're talking about the principal square root, but there really are two. As for the cube root or third root of 343, that's 7 because of this. You could check that on the calculator with 7 cubed. Is that equal to 343? It sure is. So vice versa, cube root of 343 is 7. So addressing one of the issues that was listed up above, if I try to take, well, I haven't shown the radical button yet. So if I try to take the cube root of a negative number, can I do it? And the answer is yes. Because if I change that 7 to a -7 and cube that, the first two negatives are going to cancel out, and the third one will leave us with the answer overall being negative. So vice versa, the cube root of -343 is -7. But the square root of a negative number, or the fourth root or the sixth root, if you have any even index and you're trying to take the root of a negative number with an even index, you're not going to get a real number, because we could take that original definition that I had at the top there and say, okay, if there's an answer, then square it, or whatever the even index is, and try to set it equal to a negative number. Well, any real number squared is going to be non-negative. 0 squared 0, and then take any two positives or any two negatives. The two negatives would cancel out, for example. So we're not getting any solutions. Now, as a little side note there, 0 to the nth, 0 times 0 is 0, 0 times two other copies, 0 cubed is 0, 0 to the fourth is 0, and so on. And remember, we only talk about an index that is a whole number starting with 2. So second root, third root, fourth root, etc. The nth root of 0 then is going to be 0. Okay, what about the square root of -16 and, sorry, not the square root of -16, we just talked about that. The negative of the square root of 16 and the negative of the cube root of 343. Well, we're going to learn in the next section about a connection between exponents and radicals. And in fact, the definition at the beginning was hinting at this. We do exponents before we multiply. So what if we do radicals before we multiply? This is really saying -1 times the square root of 16. So what if we take the square root of 16 first? That we can do. That's going to give us 4. And so the negative in front of it is saying that we wanted the negative square root in that case. And on this one, we already saw just in these last few examples that the cube roots of 343 is 7. So the negative of the cube root of 343 is -7. It would be a good idea to know the following, to remember as many as you can before you even have to grab a calculator. And I'll show a little shortcuts about some things you can do for the ones you don't remember. Here I'm showing a number from the left-hand column getting squared versus that same number from the left-hand column getting cubed. And going through at least the first 10 is good. If you can get it up to knowing the first 12, even better. To be honest, with the cubes, because the exponent is higher, I start to forget some of these. However, because from a previous class that you would have had before this one, you probably know that x cubed is equal to x squared times x, i.e. times x to the first. So for the ones you forget, if you can remember a lot of the squaring column, then if you start to forget some of the cubes, well, if you know that 4 squared is 16, but you don't know what 4 cubed is, instead of going to the calculator or doing 4 times 4 times 4, you could just do 4 times 16 is 64. It's actually that 343 that I tend to forget. And then once we get above 10, sometimes I might remember these, sometimes I might not. But again, I do know that 11 squared is 121. So then I can figure out 11 times 121 to find out that 11 cubed is 1331, and so on. I'll leave that there for a moment before continuing. To get a very short look at why we care about working with radicals, here's an example of something that shows up in statistics. I won't get into what that stands for, but say we see this at first. We could use the definition of a square root that was given at the beginning of this lesson to rewrite that this way. So notice how that gets rid of the squaring on the right-hand side. Let's say I have to have that formula written where m is alone instead of n. Well, I could get rid of the fraction by multiplying both sides by m. And then we have something multiplied to m. So we could then divide by that thing that's multiplied to m to get m alone. Divide both sides by a square root of n. And in statistics, we actually need to work with both versions of that formula, but they only, quite often, they'll only give you one version and assume you know the algebra it takes to rewrite it. And we're told in the textbook that in health, there's this formula. I forget what that was about. I think I had to do something about relating height to something else. So again, if I applied the definition, then if I needed to have h isolated, I could apply the definition of a cube root that gets rid of the cubing on the right-hand side. And then to get h alone, I could multiply both sides by 12.3, getting rid of that fraction. And then there's nothing else to do after that on that one. Because we're going to refer to principal roots when we have an even index, then for every a, if you have an odd index, you get an answer, and it is a unique answer. And when you have an even index and you're taking the root of something that is non-negative, if we refer to the principal root, then that is defined and is unique. So that means for each x in the domain that we plug in, we're getting one y out. We are dealing with functions. Remember that to evaluate is essentially saying to calculate. If I have f of x equals square root of x, and I want to evaluate when x is 144, then no extra work to do there. I'm just taking the square root of 144. And let me see if I can find that on here. It was a perfect square that was on that list from earlier, so I didn't even need to put it in, but there it is. Square root of 144 is 12. As a side note, that would tell us that 144, 12 is on the graph of y equals square root of x. I already had that typed. Nice. If I try to evaluate that same function where x is equal to -9. This is just another way of asking this question, but this time x is equal to -9 because that's an even index, but the radicand is negative. There should be no answer. Since there's no real number that I can square, that would give me a let's make that a negative, not a minus. There's no real number squared that I could get -9. You take two positives and multiply them, you're going to get a positive. You take two negatives and multiply them, you're going to get a positive. 0 doesn't make sense because 0 squared is 0. And sometimes people say, what about 3 and -3? Well, then you're not squaring. It has to be a number times itself. So -9 is not in the domain of f of x equals square root of x. And so, although I was able to talk about a point that would be on the graph back here, if that x is not in the domain, we don't also get a point. All right. So let's say that we have a little bit messier function involving a square root. Square root of all of 5x minus 6 is under the root, and we want to plug in 2 for x. Then 5 times 2 is 10. 10 minus 6 is 4. Notice I did all that work as if that was grouped similar to parentheses. All of that was grouped under that square root. So I find out what I'm taking the square root of. That came out to be 4. I did the order of operations inside. Then I got square root of 4. And we're talking about the principal square root of 4, the positive. That's giving us 2. Based on those few examples, this should give us an idea of what we could do to graph radical functions. So here is our scheme for graphing radical functions. And the table of values, the x's we want to put in, number one, we want to make sure that when we do the work under the radical, that we get something that is going to be in the domain, and 2, something that's easy to calculate, something that we could do quickly in our head instead of running to grab a calculator and having to type in several things. And then plot the points. And usually somewhere between 4 and 7 points is going to give you a good idea about how things should connect. It's going to turn out that we'll have a smooth curve. And I'll talk to you about showing arrows as well. So first, we're going to take a look at the most straightforward radical function, the square root function, f of x equals square root of x. Don't forget that f of x is a fancy stand-in for y. Okay, so what I've done is put in perfect squares since we are looking to graph the square root function. And don't forget, 0 squared is 0, so the square root of 0 is 0, working backwards. So I'm going to plot those 4 points and connect. Here are those 4 points graphed. And in just a moment, we're going to see them connected. It's going to be a nice smooth curve. And we cannot continue back to the left here because we can't take the square root of negative numbers. Over on the right, it's going to keep on going. So when drawn by hand, we should see arrows there. Arrows on the left, but not, sorry, arrows on the right, but not on the left. All right. So because of that, our domain begins at 0. It includes 0. So square bracket keeps on going to infinity, which we cannot include. And so parenthesis there, the range is the same because when we look from the bottom up, least to greatest, there's nothing until y equals 0. And then it keeps on going up. It's also worth thinking about, not a lot for the time being, but a little bit about how that graph compared to the graph of y equals x squared, which we learned to graph very recently. Similarly, let's graph the cube root function. Okay, so down here, I put in some nice perfect cubes and took their cube roots. Whereas up here, I took the negatives of those, which are giving me the negatives of those cube roots that I found down here. So I'm going to plot negative 27 comma negative 3, negative 8 comma negative 2, negative 1 comma negative 1, 0, 0, 1, 1, 8, 2, and 27 comma 3. And then I'm going to connect with a smooth curve. So what's that going to look like? It should look kind of similar. Again, think about this, but not too deeply quite yet. We just very recently learned how to graph y equals x cubed. And now we're seeing y equals cube root of x. And we see something climbing, but nowhere near as steeply. So notice that we're seeing a piece everywhere left and right. And it's not as obvious, but if I zoom this out very slowly, we will get higher and higher values. It's going to take quite a while, but I could take the cube root of a very large number and get 100, for example. To test that, let's find out what, you might be saying, sorry, just never even getting up to 100. Okay, well, 100 cubed, see how many zeros we have there, 6 of them. 1, 2, 3, 4, 5, 6. Okay, so let's take a look at the calculator. Let's quit out of this. And cube root, let's see, how do I get the cube root to show up? Let's press second and this button. All right, we don't want to have that. We want to first tell it that it's going to be a cube root, then second, and this button. So see what it did with the 3 on this newer calculator. Put it up in the index, and I'll put in 1 million, which is 1 followed by 6 zeros, as we just saw. That does give us 100. So sooner or later, that's going to get up to 100. And I could pick something even bigger that'll get us up to 200 or 1,000,000. So what I'm talking about is the y values. What do we see for the range? Well, the domain is all real numbers, because we were seeing a piece everywhere on the left and the right. And the range is also all real numbers. So negative infinity to infinity. When done by hand, we should see arrows at either end. So one more thing. if I remember right. Let me double check. One more thing that is, there's more than just the graphing to look at though. Okay, so 2 examples back, we saw how to graph y equals square root of x. Now we're going to graph y equals square root of x plus 3. Notice that the 3 is outside of the square root. So what we could do is take the x's and y's that we had previously, and because I was making that connection of roots to exponents very briefly, that we'll look at a lot more in 7.2, in section 7.2, we're going to tweak these. These were our original y values, but we're going to add 3 to all of those. So look at the first and third column to see which points we're going to plot and then connect. I make the claim that what this is going to do is, compared to the graph we saw previously for y equals square root of x, that this is going to shift that whole thing up by 3 units. All right, so here are the 4 points that I said I would plot. In fact, I'll let you see that I'm on a site that actually lets me type in the formulas. That's what we originally graphed. And now when we graph y equals the square root of x plus 3, with that plus 3 outside, then it is indeed connecting with a smooth curve, the 4 points. So no, although I'm using this site, it's not doing all the work for me. I did figure out the 4 points that would be on there, and it would give me a good idea of how to connect. Now notice that the original graph, y equals square root of x, had a domain and a range that started and included 0, but then went to infinity. The domain of this new function will start and include 0, square bracket at 0 and keep going to infinity. But the range now has square bracket 3 and goes to infinity. We're going to see an arrow to the far upper right there with this blue curve graphing y equals square root of x plus 3. Okay, I want to state and then kind of give some explanation as to what's going on here. Roughly speaking, having something raised to the nth power and then taking the nth root of that, if we think about the definition at the very beginning, we should be thinking roughly that they're going to cancel each other out. But because when we put an even index, we had 2 possible square roots, for example, or 2 possible 4th roots, then what's going to happen here, when you raise either a positive or negative to an even power, you're going to have a positive here, and then you take the principal root in the principal nth root of that. Then if you started with a negative, that's going to get rid of that negative. So we would have the absolute value of a. Whereas if n is an odd index, then nth root of a to the nth, they really are canceling each other out, and we just get the a. So square root of 16, we're talking about the principal square roots. Of course, the principal square root is 4. When I write 16 as 4 squared, I'm seeing that square root cancel out the squaring. Since it was already positive, then absolute value of positive 4 is 4. But here, since negative 4 squared is 16, and the principal square root of 16 is 4, then both 4 squared and negative 4 squared, when we take the square root, we're getting positive 4. We're getting the absolute value of what we squared and then took the square root of. Here with an odd index, they are going to cancel each other out. Cube root of 27, same as cube root of 3 to the 3rd. That's going to be 3. Same over here, even though it's negative. The fact that it's an odd index, cube root of negative 27 is negative 3. So since negative 3 cubed is negative 27, these are canceling each other out. We just have negative 3. If I type this into the calculator, which is not really my main goal, but to confirm something here, I'm going to put in square root of 49/4 and enter. I'm going to press, let's see where it is on this calculator, right there. Second and above table, that FD with 2 arrows means converting back and forth between fractions and decimals. It's the same as 7/2. As we'll learn about more in section 7.2, you might think that we could split up that square root across the division. Take the square root of 49 and take the square root of 4 to get 7/2. Turns out that's going to be true. So what we could have done, since we don't know what's going on in section 7.2 just yet, we could have said, well, that is 7 squared over 2 squared. And we do know that with exponents, we write that as 7/2, all of that squared. Then taking the square root is going to cancel that out. And no absolute value needed there, although it is occurring, but that's a 7/2 already positive. So absolute value of 7/2 is 7/2. Here with this even index, sorry, odd index 3, then the cubing is going to cancel out and we'll get negative 3/4. Notice that 3 cubed is 27 and 4 cubed is 64. So it's a similar kind of rewrite to what's going on right there. I talked about this a little bit earlier, but when you multiply things with the same base, add the exponents, you raise something to a power, and then you raise all of that to a power, you multiply the exponents. And let's see here if I can get that symbol to show up. Times sign. We can talk in class about why those rules work if needed, but what's that going to help us do? Well, if we have the square root of x to the 6th, if I could see x to the 6th as something squared, then I could simplify, just like we did with those numerical examples. I could simplify when we have variable expressions. The squaring and the square root will almost cancel out, but we don't know if what we have inside is positive or not. So I would have the absolute value of x cubed. On this one, looking for 15 as some power of 3, well, I'm seeing a to the 5th cubed. That's a to the 15th. So the cube root and the cube will cancel because that is an odd index. No absolute value needed. With cube root of y to the 12th, I would write 12 as 4 times 3 or 3 times 4, one of the two. Let's see here. I already had that there. Sorry. Let's give that a little more space then. Okay. So since our typo. Okay, this is, let's make it a 4th root. like we have over here. Then I'm seeing 12 is 3 times 4. So y cubed raised to the 4th power is y to the 12th. Roughly speaking, those 4th root and 4th power will cancel, but we don't know if y cubed is positive or not, because we don't know what we're putting in for y. So absolute value of y cubed, and get that symbol to show up nicely. So value of y cubed. Absolute value of y cubed. There we go. Okay, I did do a little bit already. I've shown where the square root symbol is, and I showed how to take either a 3rd or 4th roots, where I typed the index first, pressed second, and went above the exponent symbol, the caret symbol there. I've already shown the square root of 49/4. When I turned that back into a fraction, I got that 7/2. So let's see here. Let's check this real quick. We had solved this formula to get m alone. So say that we are putting in n equals 139, z star is 1.96, and that funny symbol is a little Greek sigma 3. So let's type this in, 1.96 times 3 for that sigma, and divide by square root of 139. Oops, I'm missing my division symbol. Divide by square root of 139. And that's going to give us 0.4987 something. Watch for directions about rounding. And another one that we rewrote a formula. Let's see, say we put in 216 for t and then multiply it by 12.3. I could either say, okay, index of 3, cube root of 216, which is 6. Actually knew that was going to happen. And then multiply by 12.3, or 12.3 times, let's see if this will work. I wanted to take this 3 here as an index. Okay, good, it does. Type it in all at once, and I'm still getting 73.8. All right, getting near the end. I'd already shown this about the classic mode, how it might appear, and it's not really doing that. So 4th root of 625, already know the answer is going to be 5. In this nice math print mode, type that 4. Then 625 is the radicand, that gives me 5. If I switch the mode to the classic mode, fourth root of 625, it doesn't look as nice. It is telling us it's going to put 4 in for x up here as the index and give us that answer of 5. Now, how did I know it would be 5? Well, 5 to the 4th power is 625. I know what 5 squared is, and I know what 5 squared is 25. I also know what 25 squared is 625. So that should give you an idea, roughly speaking, of how I knew that the 4th root of 625 would be 5. And by the way, we were talking about the principal 4th root there. Okay, we're going to look at one more thing. And I typed in this part here. I did 5 to the 4th to get 625 as a check. Okay, we're looking at one more example, which comes from the homework. And we're told that the distance d in miles that someone can see. Of course, the Earth is not flat, but because it's large enough, it's difficult to see the curvature. We're told that somebody stands up on, let's see, on a hill. So how far are they going to see? And let's see here. The person is on a hill that is 66 feet high, but also that person is tall enough where their feet are 6 feet above that. So the height is actually 72. Hopefully I'm reading those numbers correctly. And we multiply that by the 2 that's underneath the square root. We take the height times 2. It's going to give us 144, which is a perfect square. Its square root is 12. And just so that you can see that on the calculator, taking the square root of the answer, I'm going down to the, I press second and then to the bottom left, which you can't quite see that. Getting 12. So they would see 12 miles if they are on a hill that is 66 feet high and their eyes are above the top of the hill by another 6 feet. And it's good. All right. Hope this wasn't too long. That's all I've got for now. We'll see you in class.